In most capacitors, a non-conducting material is placed between the two metal pieces that make up that capacitor. There's two reasons for this. For one, the non-conducting material prevents the pieces of metal from touching each other, which is important because if the pieces of metal were touching, no charge would ever get stored since you've completed the circuit. But there's another bonus to inserting a non-conducting material between the plates of a capacitor. It will always increase the capacitance of that capacitor. As long as the material is non-conducting, it doesn't even matter what it is. As long as you don't change the area or separation between the plates, inserting a non-conducting material will always increase the capacitance. The name we give to non-conducting materials placed between capacitor plates is a dielectric. But why does a dielectric increase the capacitance? To find out, let's look at this example. When you hook up a battery of voltage V to a capacitor, charge will get separated. Now let's say you remove the battery. The charge is stuck on the plates since the negatives don't have a path in which to get back to the positives. So even after removing the battery, the charge on the plates is going to remain the same. And the voltage will also remain the same as the voltage of the battery that charged it up. Now imagine placing a dielectric in between the plates of the capacitor. The dielectric material is made out of atoms and molecules, and when placed in between the plates of this charged up capacitor, the negative charges in the dielectric are going to get attracted to the positive plate of the capacitor. But those negatives can't travel to the positive plate since this dielectric is a non-conducting material. However, the negatives can shift or lean towards the positive plate. This causes the charge in the atoms and molecules within the dielectric to become polarized. To put it another way, the atom kind of stretches and one end becomes overall negative and the other end becomes overall positive. It's also possible that the dielectric material started off polarized because some molecules are just naturally polarized, like water. In this case, when the dielectric is placed between the charged up capacitor plates, the attraction between the negative side of the polarized molecule and the positive plate of the capacitor would cause the polarized molecules to rotate, allowing the negatives to be a little bit closer to the positively charged capacitor plate. Either way, the end result is that the negatives in the atoms and molecules are going to face the positive capacitor plate, and the positives in the atoms and molecules are going to face the negative capacitor plate. So how does this increase the capacitance? The reason this increases the capacitance is because it reduces the voltage between the capacitor plates. It reduces the voltage because even though there's still just as many charges on the capacitor plates, their contribution to the voltage across the plates is being partially canceled. In other words, some of the positive charges on the capacitor plate are having their contribution to the voltage negated by the fact that there's a negative charge right next to them now. Similarly, on the negative side, there's just as much negative charge as there ever was, but some of the negative charges are having their contribution to the voltage canceled by the fact that there's a positive charge right next to them. So the total charge on this capacitor has remained the same, but the voltage across the plates has been decreased because of the polarization of the dielectric.